All right, welcome again. So welcome to our seminar series, the GeoSLU seminar series for the spring of 2021. My name is Henning Lozebusch, and I'm the Director of Business Development and Outreach at the Geospatial Institute, and I have the great pleasure to be joined by Dr. Phillips today, who will be moderating the questions. So why do we do these seminars? It's a platform for an exchange of ideas. It's to give our students an opportunity to see the other work going on at St. Louis University. It's an opportunity for our partners to get an idea of the breadth and depth of the research that we have going on. So in that spirit, please make sure that you use the Q&A box to ask your question as we go through the seminar here. You might even be able to join the conversation if you're interested and raise your hand, although that will be up to the discretion of the moderator, which is Dr. Phillips today. The session is recorded, and know that you can actually look at the 4 previous sessions on our website, the same spot where you actually registered for today's seminar. You can see the recorded versions of some of our really cool previous presenters. So let me just give you a real brief overview of the Geospatial Institute. We were born out of the Big Idea competition started by the Office for the Vice President for Research and Partnerships. And you can read more about these Big Idea Institutes on their website at slu.edu/research. The mission for the Geospatial Institute itself is to understand our changing world for informed decision-making on the ground and from above, connected together through space and time. And our vision is to build a regional hub and internationally recognized center of excellence in geospatial science through impactful, multidisciplinary, innovative research, education, partnership, and services. And we're really a positive force in this growing geospatial ecosystem here in St. Louis. In fact, in my opinion, St. Louis is the right place to be, and now is the right time to be here for geospatial. There's just so much amazing momentum and energy between academia, industry, and government. Our institute is built on 3 pillars: the research pillar, the education pillar, which is our academic programs. The presenters today are part of the academic programs, but also professional development through our workforce center at St. Louis University. And we also offer some data services. So these geospatial technologies are really amazing tools to facilitate research and sometimes even enable new ways of looking at our research data across so many different disciplines, from global water, energy, and food security, to climate change, to disaster response, to public health and healthcare delivery, countering wildlife trafficking. The possibilities are almost endless. And that's what this seminar is about, is to give you some ideas of the work that the students are doing here. So if you'd like to learn more about the Geospatial Institute, you can sign up for our updates. If you're a student, you can do so by going through our website at slu.edu/GeoSLU. Click on the Education and Training tab, and then you can sign up down here on this little link. If you'd like to get general updates, you can go to our website at slu.edu/GeoSLU, and just at the bottom left, click the subscribe to get the GeoSLU updates. And we try to be pretty sparing with this and not pollute your inbox with too many emails. So let's get to the good stuff here. We have 2 great presenters today with 2 great topics. But to introduce them, I will ask Dr. Phillips to join us here on stage. He's an amazing professor in GIS, who is teaching a number of our courses, actually. He also happens to be the coordinator for the master's program in GIS and the GIS certificates. So he could answer those questions as well. All right, Zach, the stage is yours.
Thank you very much, Henning. I almost don't need to introduce myself. So without further ado, it is my pleasure today to introduce Kimberly Carver. Kim is a imagery intelligence analyst for the National Geospatial Intelligence Agency. She is a recent grad of SLU in the Bachelor's of Science program in Strategic Intelligence with a minor in psychology. She's currently enrolled in our master's program in Geospatial Information Science, which her focus is the application of data analytics and computer programming to the field. Kim is also a veteran of the Air Force, which she served 8 years as an electronic warfare specialist on the F-15E, EC-130H Compass Call, and C-40C. So without further ado, today it is my pleasure to introduce Kimberly Carver. Kim, go ahead and take over.
Thank you, Zach. Hello, I am Kimberly Carver, and today I will be presenting my study on remotely sensing differences in vegetation health. This study was done as part of my final project for the Introduction of Remote Sensing class in fall 2020. I chose change detection in vegetation as an exercise for working with raster data and applying different analytic techniques, such as band combination and the NDVI, or Normalized Difference Vegetation Index. Situated at the convergence of the Mississippi and Missouri rivers, the St. Louis area presents a challenge for agriculture as the effects of climate change continue to threaten farmers' livelihoods. In the same breath, we are living in an unprecedented moment for technological advancements in remote sensing, which could improve our understanding of vegetation health and help forecast crop management. For this study, I used optical remotely sensed data from June and July 2018 to explore the following line of inquiry. What is the result of weather in June and July on agricultural crops around St. Louis? Specifically, is there a distinct difference in vegetation health between images acquired in June and those acquired in July, early in the growing season? If so, do differences in vegetation health correspond with precipitation data? The expected outcome of the study was that healthy vegetation would appear bright green in false composite images, and that there would be more healthy vegetation in July than in June, corresponding with rainfall records. The following slides present products with which to make this determination: visual comparisons of band combinations, a supervised classification, and a focused NDVI study. Here's the study area we will be exploring today. In this image, there is a point in the bottom right corner indicating the city of St. Louis. The rivers in the image appear muddy brown. You can see the Mississippi River curving around St. Louis to the east. If you follow the Mississippi River north, you can find the study area, marked here by a red rectangle, where the Mississippi and Missouri rivers meet. This is predominantly St. Charles County, and the expanse of land that sits between the rivers is largely rural, making it a great location to study changes in vegetation health. As previously mentioned, Landsat 8 imagery was used in this study. So here's a little bit about Landsat 8. Landsat 8 was launched in 2013 as a replacement for Landsat 7. Its orbit is sun-synchronous near-polar, meaning the satellite orbits Earth in a synchronous rate with the position of the sun. It takes 16 days for Landsat 8 to come back around to image the same location again. Landsat 8 has 9 spectral bands supported in the Operational Land Imager module to include visible red, green, and blue, near-infrared, short-wave infrared, and panchromatic bands. Landsat 8 is also equipped with a thermal infrared sensor, which provides 2 additional spectral bands in thermal infrared. The data from these bands is packaged into imagery that can then be accessed by the public via the USGS application GLOW-Viz. And coming soon, Landsat 9 will be launching later this year. I accessed Landsat 8 data over the greater St. Louis area for June 5 and July 7, 2018. When selecting data for the study, only scenes with 10% cloud cover or less were deemed viable. Here's the tile imagery for June 5. And here's the tile imagery for July 7. From these images, it's hard to tell which has better vegetation health, so I applied the following analytic techniques: visible comparison of band combinations, a supervised classification, and a focused NDVI study. I started with the whole tile for each data set. These are traditional color infrared CIR images of the study area collected by Landsat 8. The bands in this composite are near infrared NIR band 5, visible red band 4, and visible green band 3. These images were processed with NV 5.6 software. The selected bands correspond in that order with NV's 3 color options for rendering imagery: red, green, and blue, also in that order. Vegetation appears bright red, while dry soil is subdued red. Water is depicted as black, and urban is bright cyan. These are true color or natural color band combination images using visible red, band 4, visible green, band 3, and visible blue, band 2. True color images are susceptible to atmospheric interference. These appear darker and more hazy than other band combinations. Thus, this product is less useful than other band combinations. These images are rendered as false color for highlighting agricultural features in shortwave infrared SWIR band 6, NIR band 5, and visible blue band 2. In these images, agricultural crops appear vibrant green, bare earth is magenta, and non-crop vegetation is subdued shades of green. There is a cluster of magenta representing the city off center right, and the Mississippi and Missouri rivers and minor water systems appear as distinct black lines winding through the tiles. Given that bright green should indicate healthy vegetation, we can see from these false color images that the 5 June data on the left appears to depict more healthy crops in the farmlands to the south of the St. Louis area, while the 7 July data on the right depicts more healthy crops in the north. That being said, it is still not clear which data captures more healthy vegetation. From the false color products on the previous slide, a supervised classification workflow was executed using training data. ENVI's Region of Interest ROI tool was used to render 5 classes: water, urban, crops, soil, and unclassified, the negative extent of the tiles. The ROIs were then applied to the imagery with ENVI's maximum likelihood algorithm, which assigns each pixel in the tile to one of the classes from the training data. In the 7 July imagery on the right, there appears to be a more even spread of pixels classified as soil. Another observation is that the 5 June imagery on the left highlights bright, healthy crops in the south. Graphs were created from the classification data. These supporting graphics may help answer the question as to which imagery presents more healthy vegetation. The graphs show the percentages of area populated by each class within the 2 images. It is worth pointing out that the scales are a little different. The June imagery has a higher percentage of healthy crops at 48% and a relatively low soil percentage at just over 14%, while the July imagery has just shy of 37% healthy crops and almost 27% bare soil. The pixels classified as urban and water are steady across both tiles. So what did we learn from the supervised classification? As I said, between June and July, there was an increase in soil area and a decrease in crop area. That is one answer, but the greater St. Louis area is big, perhaps too big. By examining the whole tile imagery, which is peppered with many variations of urban, suburban, and rural areas, the results may have been hiding, so to speak. An NDVI study applied to a refined study area, rural St. Charles County, may be a better strategy for answering questions about vegetation health. As previously mentioned, NDVI stands for Normalized Difference Vegetation Index. Using band arithmetic, we can estimate vegetation health. NDVI is the difference between the NIR band, band 5, minus visible red, band 4, and NIR plus visible red. NV has 2 tools that can generate an NDVI, band calculation and the NDVI tool. For the purpose of this study, band calculation was used. When making this calculation, each pixel is assigned a new value between -1 for poor crop health and +1 for good crop health. The results of the NDVI should provide clarity on vegetation health for our refined study area, rural St. Charles County. Here are the results of the NDVI for June 5 on the top portion of the slide, and July 7 on the bottom portion of the slide. The colors should be interpreted as follows. Purple is generally poor plant health, from yellow to white is neutral, and green pixels indicate healthy vegetation. Between June and July, there is between June and July, there is a definite increase in healthy vegetation as fields transition from white and lavender to deep shades of green. The agricultural areas between the two rivers are the best example of this effect. And natural vegetation, such as trees and bushes, remain similar between the two tile images. If we look at where the pixel values fall on a histogram, we can see even more clearly where the healthy vegetation is measured between the two images. Here, water and urban areas remain consistent. June presents a significant proportion of bare ground and young plants, while July data reveals more healthy vegetation overall. This may be due to a few relatively big rain events in late June 2018, which we will look at next. So how do these findings measure up to the weather data from the National Oceanic and Atmospheric Administration, or NOAA? These graphs were created from the St. Louis monthly weather data as reported by NOAA's National Weather Service for June 2018 on the upper portion of the slide and July 2018 on the lower portion of the slide. An arrow has been placed on each graph indicating the date of the imagery. On 20 and 26 June, as well as on 1 July, there were weather events that each neared 1 inch precipitation. This likely contributed to the overall growth of healthy crops between June 5 and July 7. The expected outcome of the study was that healthy vegetation would appear bright green in false color composite images, and that there would be more healthy vegetation in July 2018 than in June 2018, corresponding with rainfall records. The actual outcome is a little different. First, healthy vegetation did appear bright green in false color composite imagery. However, after a supervised classification, the result seemed to suggest that there was more healthy vegetation in the June imagery than in the July imagery. And this may have been a consequence of using the whole tile as opposed to a refined study area targeting the agricultural domain. An NDVI study revealed consistency between the expected outcome and the actual outcome. There was more healthy vegetation in agricultural crops in July 2018 than in June 2018. Moreover, these results correspond with NOAA's precipitation data. Recommendations for improving the accuracy and precision of remotely sensing vegetation health include advancements in machine learning and artificial intelligence, AI, using hyperspectral and SAR applications, and trying different temporal resolutions or revisit times and different look angles that provide agility to custom collections by the use of unmanned aerial vehicles, UAVs. And now I can take questions.
Thank you very much, Kimberly. There is a question from our Q&A box. Considering that different crops grow at different times at different rates, is it important to consider, or can you tell the different types of crops within the study area?
Sometimes you can. It depends on the kind of leafing that the crop has. So the way that it presents its leaves, its vegetation. Some of the studies that I read about, they use some of those different applications, such as hyperspectral and SAR applications, to try to detect those different crops and see how they are faring at different times of the growing season. So that's one way that we can expand that study.
Excellent. And a question from me for you. We only really consider rain as being the significant driving factor between vegetal growth. Can you talk about some of the other possible sources of, enhanced vegetal growth during this period?
Yeah, so one of the issues with vegetation health is making sure that it has the right nutrients. And sometimes those nutrients are leached through the soil over the years. Sometimes there's a different proportion of nutrients that's not conducive for certain types of crops. So like nitrogen and chlorine and things like that. Those are critical to ensuring that crops have the right kind of nutrients, those minerals in the soil. And then also, if there's a lack of rain, that can also affect it. And if you're trying to grow the wrong kind of crops in the wrong kind of the wrong kind of area, that can also make it difficult for those crops to thrive because they're not used to the ecosystem. And then if there's invasive species, that can also be a problem. So there's many different factors.
Yes, very complex system we deal with.
Yeah.
Are there any other questions from folks in our Q&A box? Please, I will leave the floor open for 10 more seconds here. All right, well, thank you very much, Kimberly. That was excellent. I really appreciate you showing off your work from intro to remote sensing. This is fantastic.
Thank you.
All right, our next speaker today, following along with the theme of vegetation, shifting over from vegetation health to vegetation recovery. It's my pleasure to introduce to you Eric Suter. Eric is a second-year computer engineering student with career interest in signal processing, RF, and remote sensing and geospatial. For anybody out there hiring, sadly, not sadly for Eric, I'm sure, but Eric is working this summer as an intern on campus to further develop a nano satellite for an experimental launch to a low Earth orbit. So if that seems like a talent you might want to hire in the future, this might be your guy here. Eric took my GIS 4040 Intro to Remote Sensing class last fall, produced a really nice final project centered around vegetation recovery after the recent wildfires in California. So without further ado, I present to you Eric Suter.
Thank you so much, Henning, for setting up the program, and Zach for the warm welcome. But yeah, my presentation today is on the post-wildfire vegetation recovery, specifically focusing on the rim fire in California. So a little bit of background on the rim fire. So it began on August 17, 2013 as like a small human-caused fire. It's unsure of the exact cause. It was maybe like a campfire or a cooking fire or something like that. But it grew very, very quickly. Just in the first day, it had already spread to 1,000 acres, 10,000 acres in 3 days. And by the end of the week, it was up to 100,000 acres. It was finally contained for the most part around September 27th, but it continued burning. It was completely contained in October, but there was still some smoldering in the ashes up to over a year later in November 2014. The total cost of the rim fire was approximately $125.8 million. There were around 100 structures destroyed, and thankfully, because it was in such a remote part of the state, nobody died. So we can be thankful for that. But here, the image on the right is the rim fire while it was burning sometime in early September, late August. But it is the large fire here in the center on the eastern portion of California. And you can actually see another fire here at the upper left. That is the American fire in Placer County, which this fire is a little bit more typical or average in California's wildfire statistics. It burned about 20,000 acres, which is around average, maybe a little below average for a normal year. So as you can see, the rim fire here in the center is just so much larger and was so much more devastating. And the image here on the left, this is from the GeoTIFF data that I downloaded and used as part of the project. And this was one that I thought was interesting because you can see the fire still burning. So as you can see, California's wildfire problem, as you can hear from the news as well, just continually gets worse. So at the time, the rim fire was the third largest fire in California history. But as you can see, looking at the charts, that is no longer the case. Because of some very devastating recent fire seasons, The rim fire is now down to 10th, where it was in 3rd as it burned. And just dominating this trend is, or was, August of last year, which just was a completely devastating fire season. As you can see, the #1 fire, the August complex, burned over 1 million acres, just completely devastating the area, and so much larger than all the other fires, more than double the next. And 5 of the top 10 fires were all from last season. So as you can see, this is a worsening trend and will probably continue to worsen as climate change and other factors ramp up. So yeah, climate change in California is also in a severe drought, has been for years. So this is all contributing to the fire problem that's going on, which really begs the question, if California is having all these fires, how long is it going to take the vegetation to recover? Because if the whole state is burning, how long will it take for the whole state to be completely burnt? So that's where the subject of this study comes in. So the data that I used was the Landsat 8 multispectral imaging. And just a little bit of background, Landsat is a partnership project between NASA and the United States Geological Survey, where they'll send satellites into space in a sun-synchronous orbit, so they're always taking pictures of the day side, where they will make a catalog of the entire Earth around, I want to say every 2 weeks is when it completes like a full orbit and it takes a picture of the same area again, just for public data and for research purposes, and anyone can use it. I downloaded it for free at the USGS GLOVIS web app, which is really nice. And the way multispectral imaging works is that you have several different bands. In the case of Landsat 8, there are 11 bands, each with a different frequency or wavelength. So on the right is the wavelength in micrometers. So like band 1, that's 0.43 to 0.45 micrometers, or another unit you might have heard it in are nanometers. So 430 to 450 nanometers. And there's some bands that you'll probably recognize, like blue, green, and red, and bands 2, 3, and 4, around like 450 nanometers to all the way to 670. That's the visual spectrum of what we're able to see with our eyes. But there's so much more useful information outside of that. So obviously there's the coastal aerosol above, but then there's also a huge area of the electromagnetic spectrum that we can't see, but is still useful to us. A lot of this is infrared. You can see there's some other bands like cirrus, which is good for measuring clouds, thermal infrareds for temperatures, and that sort of thing. So using the USGS GLOVIS web app, I downloaded the multispectral imaging data for the rim wildfire location in Stanislaus National Forest. So I went to that location, and then for every year following the fire, around the same time, unfortunately, you cannot, the way the orbit works, it's not going to fall on the same day every year. So you have to choose a day approximately when the fire was. And also, if it was a very cloudy year, you have to find a different image a few weeks earlier or a few weeks before. And the images on the bottom left, these are what I would use for the study. These are false color. Obviously, they're not red trees in California in this area, but these are in bands 5, 4, and 3. So in the color red is near infrared, which is band 5 over here. Green, which is band 4, is actually in red, which is all the trees are red. And band 3, which is blue, in this picture is being represented, or blue is representing the green band. All right, so for the pre-processing of the data, the first thing that I did after downloading was just a quick atmospheric correction, because the atmosphere can introduce some unwanted variables and some clouding, that sort of thing. So just a quick atmospheric correction to take that out. And the next part was the creation of masks. So I only was interested in the areas that were burned. So I made a mask of the full and the worst extent, which I thought was an important distinction. So as you can see in the image here in the middle, this is the entire fire location. The white areas were the worst burn areas, and the darker areas were where the vegetation was singed or not completely burned. So I thought it was important to contain this whole thing, which is over here on the left. This is the full extent. And then on the right is the worst extent. So you can see the much brighter areas are featured in the worst extent, while some of the darker areas, which is right here, is missing in this image. And it was an important distinction, to me at least, because you want to make a note of just how awful the worst areas that were hit, how long it took them to recover, as well as how long it took just the general area to recover. So in actually processing the data, was using, again, the ENVI software that we used in that class, the image change workflow, which is a wonderful workflow where you can submit 2 images, an initial image, which in this case was the pre-fire image before the fire and all the burning, and then the post-fire image. So in the cases like below, where the 2013 data, this is where the post-fire image taken on September 16th was compared to the pre-fire image sometime in mid-August. And the way that it works in ENVI is that it calculates the burn index on the image change. So it calculates the burn index using the formula band 4 from the previous page, band 4 minus band 7 over band 4 plus band 7. And this spits out like one number, as you can see in the burn index on the images. It spits out one number, which is the difference between the two. So how much a higher burn index indicates a much worse burn than a lower index would. And as you can see, in the worst extent, there's a burn index of 0.69, whereas in the full extent, it's only 0.435. And so this was the data that I ended up with. After doing the image change workflow for every year or every season after the fire, I used the image change workflow to get an image and a burn index, and I compiled all of these separate years into one animation, which is here. And as you can see, as it goes throughout the years, I've got the date there, which will be important later, as you'll see. But throughout the years, the area slowly becomes darker and the burn index goes down, which is good. That's an indication that the vegetation is healing and that it's recovering from the wildfire. But there are some jumps. If we follow it again through, it starts high in 2013, goes lower in 2014, a little bit higher in 2015, same around 2016. It goes a little bit higher still in 2017 before it starts dropping in 2018, which is good, that shows that it's healing, but unfortunately in 2020, it goes up a little bit more, which was kind of concerning. And we can take a look at here in a second. So outside of the animations, here's just a graph of the raw data that I plotted. And as you can see, generally, the worst extent is above the full extent, the worst extent being in orange and the full extent being in blue. And they start out very separated in the early years, like especially right after the fire in 2013. And over time, they converge and become much closer, which is good. It shows that the worst extent is healing to match the full extent over time. And I also have 2 little trend lines to show generally how it's moving over time in the worst extent and the full extent. And so these little equations are what can be used to model and extrapolate where the fire may end up in some years if it keeps continuing at this rate. So the worst burn should, according to this model, be recovered around 2024 in the best case scenario, which is much, much different. And you can see where some of the error in extrapolation comes when the full extent recovery will be around 2031, which is several years longer. And those, obviously more data is needed to help refine the predictions, but that's where it stands right now. But the data is still a little bit concerning. As you can see, there are big jumps that I pointed out with the animations, and you can see them here too, where it goes from much higher to lower and then mysteriously back up again. And that really concerned me. I wanted to know why this was happening because logically it just shouldn't. So my first thought was that it could be the time of day. So the satellite, remember it's a satellite collecting all this data, and we don't have control over the orbit. But when I looked in the image metadata, looking to see if it was maybe one was taken in the afternoon, one in the morning, and if the sun would have a difference being where it is in the sky, after digging through the image metadata, this was actually a non-issue because all the images were taken between 639 and 641 for each year, which it's good that the orbit does this so that the data can be as close as possible to one another. So after ruling out the time of day, my next thought was maybe if there was like a storm, like some rain for the vegetation to heal a little bit more with right before the images were taken. But after doing some digging in California weather data, especially for Tulum County, it turns out that it hasn't rained in August in that area since before the fire. So that takes some of that out too. So then after the two easy options were out of the way, it took a little bit more digging. So my next thought was, could it possibly be with the days apart that the images were taken? Because the initial image was in August, but some of the later images had to be later because of clouds or earlier, because you can't always get a clear image when you want. So taking a look at that, I have in this table to the right, the year that the image was taken and the difference in days from the 2013 pre-fire image. So obviously in 2013, there's going to be a huge difference because at the 2-week point, there was that's when the fire was still going on. You couldn't see very much because of the smoke. But then after the smoke had cleared, that was about a month later. So that was the first image used. And the same process was repeated for the remaining years. And as you can see, most of them are later, some are a little bit earlier, but they're around the same threshold. So I plotted that on the same graph as with the full extent and worst extent data. And the data makes sense a little bit. I don't have a way to quantitatively compare them, but just looking at the graph, it kind of makes sense. So especially you can see it down here, like with the -5 and the -10 area, these are where the image capture of that year was days before the image capture of the pre-fire image. So it makes sense. It's still in summer. It's still hotter. It hasn't had as much time to recover. So the recovery data has a high burn index, which makes sense. And then if you go later in years, you'll have these images that were taken much later, 2 to 3 weeks later than the pre-fire image. And as you can see, they have, especially in this case of 2019, it has a very low burn data, which makes sense because in 2019, it was taken 17 days after the same date in 2013 of the initial fire. So it would have more time to recover. And especially that's when that area starts getting more rain in the fall, like September. So that makes a little bit more sense. But I still wasn't sure. So I wanted to look in other areas. So the next area that I looked were in the drought conditions of California. And so there's a wonderful website, drought.org, that keeps track of drought in California and the whole country. But it's especially important in California because of all the fires. And so at the bottom right, here's an image, like a sample of what the website has. You can select a county and it'll give you the burn data as a percentage. So drought.gov measures it with different burn intensities. So it starts with a burn intensity of 0, which is where it's just like a little bit drier than normal, but nothing major. And drought level 4, which is where it's terrible drought conditions, like near historic levels. And it gives a percentage for each. And as you can see, well, I should also point out that over here, you can see the different levels. The darkest area is D4, the worst extent, and the yellow is the much less severe extent of D0. So, and these are percentages, but I wanted to keep them as a percentage instead of converting to decimal, just to make it a little bit easier to see on the graph over here. We have the sum of the percentages, which is in this column of the table for each year, plotted again with the full and worst extent data. And there's a strong correlation, as you can see, a little bit fuzzier towards the beginning, but it starts to match up towards the end. So you can see when there's a much worse drought in the 500s area, there's still a high burn index. Obviously 2013, that's when the fire was just done, so it's not going to make a huge difference, but it roughly follows the recovery of the vegetation, especially in the later years, which is a much better indicator in my opinion, than the days apart, because with drought conditions, it takes into account more than just rain, which was my initial starting point, with things like seasonal rain, not just rain in, say, the couple weeks beforehand, but also the seasonal rain and other conditions like dry winds. And this was a much better indicator. So some conclusions I have to draw from this study is that multispectral imaging can be used to quantify the recovery of vegetation after the 2013 rim fire and other fires like it. Over time, the burn index generally decreased, which is good, what we want to see. Over time, it makes sense that the vegetation would recover. From extrapolating from the worst burn extent, the earliest possible recovery is in the year 2024, although that's unlikely to happen. That's a very best case scenario. And the last conclusion we can draw is that the worst burn extent index started much higher, but then over time, the two values converged, the worst burn extent and the full burn extent, which makes sense. So the worst burn extent heals more and eventually converges, and they heal at the same rate. All right, thank you. That is the conclusion of my study.
Excellent. Thank you very much, Eric. Great talk. Got a couple questions for you. First of all, want to know if we can use GIS and remote sensing to be proactive about this sort of thing and fight the fires before they start.
Absolutely. GIS is such an important technology to utilize in so many sectors. And in this study, it was used to show the recovery of vegetation after the fire. But we can also use the same technology to see the moisture in the crops. And as Kimberly was showing earlier, the health of the vegetation before we even get to where we have to recover from a fire. So yes, GIS is a very, very important technology with many applications.
Excellent. Our next question, more of a procedural sort of question.
Yeah.
So we want to know more about GLOVIS. How do you access data? What are the different features like of GLOVIS? And how did you come up with the idea for this project?
Okay. GLOVIS is a wonderful, wonderful application hosted by the United States Geological Survey. It is a free portal that you can use where they have, in this case, I use Landsat 8, but they have data from every Landsat satellite for all over the world. You can think of it almost like a Google Maps, sort of, or Google Earth, where you can zoom in on the area in particular you want, but you can also download that data. So the way that it works is that they have specific like plots almost for each area. And a plot would be a little bit larger than this image, like a square. And then they host the image data on that online that you can download. And a TIFF, it sounds kind of complicated, but it's actually just like a normal image. Like you could open up a TIFF with a standard media player, but it's very, very dense in the information that it has. So each TIFF that I downloaded, it's a huge file. While I only used bands 543 here in these images and band 7 in the burn calculation, each TIFF you download, it's as if you're downloading 11 different images, one for each band. So I could have made a combination of any of these bands, but I chose to use the ones that are most applicable to the burn scenario in this case. But yeah, GLOVIS, wonderful website. I think you just have to make a free account, but then after that, you can get lost looking around the world and you can do your own studies just like this.
Yes, there's all sorts of filters where you can filter through data and find exactly what you want in the vast world of remote sensing data out there.
Yeah.
So how did you figure out where to find these data, or even that they were there?
These data, I can thank my wonderful GIS professor, Dr. Zach Phillips, who pointed us in this direction, because this study that I did was actually my final exam in his class. And so he pointed us to in this direction to use the GLOVIS application, because it's such a wonderful application for free data that anyone can access. And there are many, many other applications, but this one in particular had exactly what I needed. anywhere in the world, and you can find a TIFF with all of these bands for any place, really.
So our the final question that is rolling in here is, why did you not use Sentinel-2 images?
Ooh, in this case, I mean, I'm sure I could have used images from other things. I could have used hyperspectral data, which Landsat only has these 11 bands. Hyperspectral imaging has upwards of hundreds of bands, but I chose to use Landsat 8 because we used lots of Landsat data in the class that I learned how to do this in. And I also used Landsat 8 because it was launched in 2013. I want to say February, but it was launched at the beginning of the year, the same year that the Rim Fire happened. So I was able to use the newest generation of Landsat satellite for the entire life and recovery of the fire. So that's why I chose to use it. I'm sure I could have used other applications, but I was most familiar with Landsat too.
Excellent. I believe that is all the questions that we have today. Thank you very much, Eric. We really appreciate it. This is great work. And I also want to say thank you to Kimberly. These have been excellent presentations. You make me proud to have you as students. I greatly appreciate it. So without further ado, I will go ahead and turn the floor back over to Henning.
Yeah, this was fantastic. This actually makes me want to go and do the same thing at the national scale, basically, to see the effect of burns over time. I wonder how far back historically the data goes, but can you basically provide a picture of what, according to news and things you read, seems like is an increasing problem with these wildfires? No, really, really cool. And then vegetation health and the growing just made me think of my own backyard and how much more lawn mowing I have to do this weekend. I love these presentations because I personally learned so much, and it really is such a great picture of all things that you can do with these geospatial tools and remote sensing. It is really, really cool. So definitely, thank you, Dr. Phillips. Thank you, Kim. Thank you, Eric. These were great presentations. And this sadly brings our seminar to an end for today. I really do hope you enjoyed it. In 2 weeks from now, Friday at noon again, we will have 2 more presenters. This time it will be one presentation on Sport Diversity Index, Reframing Inequity in Youth Physical Activities by Kemba Noel London. And the second one will be Landscape Changes in Aegeus across the Yucatan in Mexico. Distant Drivers and Social Ecological Impacts by Ted Lawrence, who is one of our postdoctoral research fellows. So those as well should be really interesting. So please come and join us. As always, we love to hear your feedback. If you have any questions, this one seemed to also be a great promotional seminar for some of our coursework. So if you have any questions there, feel free to reach out to us. Come check us out on our website. We're always here to answer questions or have fun conversations. So all that said, enjoy the great weekend. I know there's light at the end of the tunnel right now with vaccinations and other things, but keep wearing that mask, keep washing your hands, stay safe, and enjoy the weekend. All right, thank you very much, everybody. Take care.